Hello, welcome to this lesson on empirical and molecular formulas. Today's question of the day: what are some of the differences between water and hydrogen peroxide? I just gave you one, spoiler. Obviously, they have different names, they have different formulas, they have different masses, they have different boiling points, they have different toxicity levels, they have different everything except for really the elements that they are made of. An empirical formula is something that's new. It is going to show the skeleton formula, or kind of just the basic ratio of one element to another in a chemical formula. So if we look again at that hydrogen peroxide, H2O2, the empirical formula is HO, indicating that for every one H, you have one O. The molecular formula is a formula that you have been working with this entire time in chemistry. So far, we've just been calling them chemical formulas, but it is the same thing as a molecular formula, and that is the true or actual formula of whatever that substance is. So for hydrogen peroxide, it's H2O2. The concept of empirical and molecular formulas I would say, fits in with forensic chemistry, some like investigative or analytical chemistry, not typically things that you are going to do in a high school chemistry lab a lot of the time because the materials and just the lab equipment that you need is crazy expensive. But the mathematical process here is very much related to the percent by mass. So there are a lot of teachers who will teach it in a high school setting. Truthfully, it's not my favorite. I don't love it, but I have found that a lot of my students actually really like empirical and molecular formulas. So let's say that we're looking to get an empirical formula from a molecular formula. In order to do that, you just reduce the subscripts until they can't reduce anymore to figure out their simplest ratio between each of those elements. So here's just some practice. Across the top, we have molecular formulas, which are just real formulas. And beneath them, we have their empirical formulas. So you will notice that ammonia, NH3, has the same empirical and molecular formula. All that means is that the molecular formula is already reduced as much as it can. It's just a very simple molecular formula. That's all. And then we have some other examples here where we are reducing. Again, here is CH2O. There's no reduction at all because the molecular and the empirical are the same. And then over here, we are dividing everything by 2 in order to get the empirical formula. Molecular formulas are a little bit tougher. These are 6 different molecular formulas. Do they exist in the real world? Honestly, I couldn't tell you. That's a question for an organic chemist, not me. But I can tell you that each of these molecular formulas has the same empirical formula. So all of these will reduce down to that CH2O that is listed up at the top left. I like to think of the molecular formula as some multiple of the empirical formula. So if this is the empirical formula for all of these substances, this has a multiple of 1, this is 2, this is all of the subscripts times 3, 4, 5, and 6. So that's kind of like the way I keep it straight in my head. The molecular is a multiple of the empirical. Now, when you try to get the molecular formula from an empirical formula, a lot of the time you will be given that empirical formula and you will be given the molecular formula's mass. And this is figured out like in the real world using IR spectroscopy, NMR, which is kind of like an MRI, but for molecules. And then you will piece these pieces of information together that you get from these different tools, and you can figure out what this mystery substance is, like its real formula, just from doing a little bit of math. And really, it's actually pretty cool. So in this lesson, I'm going to walk you through some examples because these questions can be presented in a few different ways. So in this case, we are assuming that we have 100 grams of this substance and 40.68% of it is carbon, 5.08% of it is hydrogen, and 54.24% of it is oxygen. And the question here is, what's the empirical formula? We're going to assume we have 100 grams of this simply because we can. Percentages are easy. It's kind of like a piece of a pie. And if we're working with 100 grams and we're working with percents, then 100 is a logical choice to make our assumption from. And then from here, because 40.68% of 100 is 40.68, that would mean we had 40.68 grams of carbon out of the 100 total. If you are given grams from the start, you just skip this step of converting the percent to grams because you're already given the grams. So here we are making that quick conversion. We're just converting the percentages directly into grams. Of course, this is because we have assumed that we have a 100-gram sample. The next thing we're going to do is convert those grams into moles using a ratio, and this is for carbon specifically. So we're just going to pull that 12.01 directly from the periodic table, and the 4.68, of course, comes from the question, and we want to find out how many moles this is. So in this case, we have 3.39 moles of carbon. We would have 5.04 moles of hydrogen and 3.39 moles of oxygen. Now, you and I know that you can't have half an atom or a quarter of an atom or anything like that. You have to have a whole number of atoms. So we're going to take all of those moles and divide them by whichever one of them was the smallest to get down to the ratio of one element to the next. So out of all of these values, the 3.39 was the smallest. So we're dividing each of these by the smallest number of moles. And across the bottom are the results, and that is going to show us the ratio of one to the next. So for every one carbon, I have 1.5 hydrogens and 1 oxygen. Now, you and I know we can't have 1.5 hydrogens, so we're going to multiply all of those by 2 to get rid of that 0.5 and kind of fix it up a little bit. So instead of having a 1 to a 1.5 to a 1, we instead are going to have a 2 to a 3 to a 2. And this represents the basic ratio of our carbons to hydrogens, to oxygens. When we put that all together, we get the chemical formula C2H3O2. And if you try to reduce any of those subscripts, you can't, and also get a whole number. So this is a perfect example of how to get an empirical formula. Getting a molecular formula is not that hard either. In this case, we have some percentages for our elements. We're working with carbon, hydrogen, and oxygen again, but this time we're given a molar mass. Our molar mass is pretty big. It's 769.24 grams per mole. It's pretty big. The question is, what is the molecular formula? So just like before, we are going to assume that our total sample is 100 grams, and then these percentages are very easily just going to convert straight over to grams. Just like this. The 84.31% becomes 84.31 grams, and so on. We're going to take those grams and convert them into moles because carbon is a lot heavier than hydrogen, so we have to put them into moles so that we can actually make fair comparisons between these things. Remember, moles are just a quantity, so we're counting. It's literally a ratio when we convert from grams into moles. So using the same setup as before, in this case, the 84.31 is derived from the question, and the 12.01 is the molar mass of carbon that we've pulled from the periodic table. If you did a QMT, it would just be 1 carbon, so no need for that. You just pull it from the periodic table. And for carbon, you would get 7.02 moles. 11.44 moles for hydrogen, and 0.26 moles for oxygen. So again, we know that we have to have a whole number when we are talking about the ratio of one thing to the next, specifically in chemistry, because you can't have half an atom or a quarter of an atom or a third of an atom. They have to come in whole numbers. So again, we're going to divide each of these by the smallest to have like that number divided by itself to get 1. This way we'd have at least 1 of something. So here the 0.26 moles of oxygen is the smallest. The 0.26 divided by the 0.26 is going to give us the 1 oxygen. And then we're going to find out what these come out to figure out those ratios. The molar mass of this substance was pretty large, so it makes sense that we would have 27 carbons and 44 hydrogens and just 1 oxygen. This is a big molecule. Putting this all together is actually going to give us the empirical formula, remember, because we would divide this we would be trying to reduce the subscripts. And if we have a subscript of 1, we can't reduce it anymore. So this in total is going to give us the empirical formula. You may have noticed that the steps up until this point were exactly the same. So the next step is going to be going from the empirical to the molecular. So we're going to do a QMT chart of that empirical formula that we just found, and we are going to divide the molecular formula by the empirical formula to figure out which multiple was used to go from empirical to the molecular. When that happens, we're going to multiply all of our subscripts by that multiple so that we can get the molecular formula. So here is my filled in QMT chart. I have 27 carbons, 44 hydrogens, and 1 oxygen. I know that for most of this YouTube course, we have not been going out so far on the mass in the QMT charts. I can tell you that for empirical and molecular formula, you're going to want to, because, I mean, even just look here, 44 times 0.008, you're getting 0.3. It's like decently significant when it comes to adding this all up. Your numbers are going to be a lot better and a lot more clear and maybe even more easy for you to understand if you go all the way out on the periodic table. So up top right here, we have the molecular mass from the question. We were told it was 769.24 grams per mole. And this empirical mass is coming out to 384.62. So when we divide this, we are getting our molecular multiple of 2. This 2 is going to be multiplied by those quantities or by those subscripts to figure out what the actual formula of this compound was. So we have our empirical quantity, which is the subscripts from the empirical formula. Our molecular multiple was 2. So our molecular quantity or our subscripts are going to come out to 54, 88, and 2 respectively. That's it. I know that this is really tough. If anything was a little too tough, I would go back, rewatch the video again, maybe pull in some questions that your teacher has for you, because this is something that certainly requires practice. I have taken years to really understand how empirical and molecular formula works. It does take some time to click. If there are any questions beyond that, please leave them in the comments below the video. Subscribe so you don't miss the next one, and I'll see you there. Bye.